If SOLIDWORKS Flow Simulation isn't already set up on your machine, it's easy to install on your own. First, you have to have SOLIDWORKS installed on your system, which you can do either from a SOLIDWORKS installation disk or by downloading the software from the SOLIDWORKS website. I'm going to assume you already have SOLIDWORKS installed on your machine, but I'd like to walk through the steps to installing the Flow Simulation add-in. These steps might vary slightly based on what operating system and version you're using, but the process should be similar. I'm using Windows 7. I'll open up the control panel and go to Programs and Features. Once the list of installed programs populates, I'll look for my SOLIDWORKS installation, right-click it, and select Change. This opens up the SOLIDWORKS Installation Manager. I'll choose to modify the existing installation and click Next. This takes me to the serial numbers step. Here, when SOLIDWORKS asks, do you have any other serial numbers, I'll make sure to enter in the serial number for Flow Simulation. I can continue walking through the Installation Manager until I get to the Downloads section. Make sure the checkbox next to Flow Simulation is checked. That way SOLIDWORKS will download and install the add-in. And just follow the steps of the wizard the rest of the way. If you're having any additional trouble getting the add-in installed, contact your SOLIDWORKS reseller for additional support. As I mentioned in the introduction to this course, SOLIDWORKS Flow Simulation is capable of performing both internal and external fluid flow analyses. However, prior to running the analysis, you might have to do a bit of setup work to prepare your model for the study. By internal flow, I mean that the flow is bounded by solid surfaces on the outside, such as flow through a pipe or duct. A good way to think about this is that the fluid enters a closed system through one or more inlets and exits the system through one or more outlets, with the exception of some natural convection problems that have no openings. For internal flows, there are two aspects of model preparation that may be required in SOLIDWORKS Flow Simulation. They are creating lids and checking geometry. An external flow analysis is one where the fluid flow surrounds the model, for instance a flow around a vehicle, rocket, or other projectile. If a flow has both internal and external elements, like the flow through a car with the windows down or flow through and around a building, for instance, then you should treat it as an external analysis. For external analyses such as these, you must set up a computational domain boundary, or an area around the model for which the flow is calculated. We'll look more at this in the external analyses sections of this course, but for this section, we'll look at the two aspects of model preparation for internal studies, lids and check geometry. To perform an internal flow analysis, all openings within the model must be covered using SOLIDWORKS features called lids. The surfaces of the lids that contact the fluid are used to apply boundary conditions that introduce a mass flow rate, volume flow rate, static or total pressure, or a fan condition within the fluid volume. Lids are required for an internal analysis, but they're usually not required for external analyses problems or natural convection problems, unless the problem requires the application of an external flow source, such as a fan. Let's take a look at how to add lids using the Create Lids command, which is by far the easiest and quickest way to create lids. Now, this definitely isn't the most realistic part, but it's pretty similar to an internal analysis we'll be performing later in the course, and it's a good example of the many different types of lids that you may need to create for a flow analysis. I'll launch the command by going to the Flow Simulation drop-down menu under Tools, and I can select Create Lids, or I can simply click the icon on the Flow Simulation toolbar. Now, all I need to do is select the planar face on the model that I'd like to close using lids. As I select them, you can see they're added to the list. Really, that's the only requirement here, is that the faces you select are planar. Notice that I can select all of the planar openings and they're added to the list. I'm unable to select the non-planar inlets or outlets. I can choose to use the default lid thickness, or I can click the Adjust Thickness button and enter a custom value for the lid thickness. For most analyses, the lid thickness isn't very important. It shouldn't be too thick to the point where it might interfere with the flow pattern downstream in any way, And it also shouldn't be too thin, especially in a combination internal and external analysis, or the mesh and cell count will be extremely high. A good rule of thumb is to keep the lid thickness roughly equal to the thickness of the neighboring walls. When I click the green check, the lids are added. You can see the 5 lid bodies are in the Feature Manager tree, and again, as long as the faces are planar, you should be able to create the lids regardless of the shape of the inlet or exit. Now, this is a part file, but if it were an assembly file, the process would be identical, except the lids would be created as their own part files, instead of as bodies within the part. If for any reason the Create Lids feature isn't working to cover the opening, you'll have to create the lids manually before running the analysis. We'll look at the process for that in the next couple of lessons. If you run into a situation where the Create Lids tool isn't able to create all of the necessary lids for you automatically, you'll have to manually close off the inlets and outlets in your system before running an analysis. This process is very straightforward, but there are a few rules you must follow. Let me show you how using this opening here. Because this outlet contains 2 faces, the Create Lids feature won't let me select it. Instead, I'll have to close it off manually. To create a lid here, I'll have to first create a new reference plane to sketch on, since there isn't a single planar face that will work. I'll create a plane that's parallel to the part at the outermost edge of the outlet. I'll start a new sketch on the plane and use Convert Entities to convert the inside edge to sketch entities. Next, I'll launch the Extrude feature. I want to make sure to select the mid-plane option here. This is very important. The blind option will create a disjointed body between the lid and the rest of the part, and this will cause an invalid contact, which we'll see later on when we run Check Geometry. Simply put, Flow won't be able to apply boundary conditions to the surface when there's an invalid contact, and we'll have to go back and fix the lid again. So I'll make sure to use mid-plane. The other important option here is make sure you uncheck the Merge Results checkbox. This will keep the lid as a separate body from the rest of the part. I'll make sure it's thick enough so that it closes off the part. When I click the green check, the lid is complete. Creating lids manually in an assembly is very similar to how you do it in a part file. The only difference is you have to incorporate some basic top-down design technique to add the lids as their own part files. To add lids to this assembly, I'll go to Insert, Component, and select New Part. I'll rename the part in the feature tree and call it Assembly Lid 1. Now I'll edit the part. From here, I can just use the same process for manually creating lids in a part. I'll start a new sketch on the face I need the lid on, use Convert Entities to convert the inner edge to sketch entities, and finally use a mid-plane extrusion to create the lid. Easy enough, right? One thing to keep in mind is I recommend creating individual lid parts for each opening you're trying to cover. That way you can apply different materials to each of the lids if you need to, which can be useful, especially if your analysis involves heat transfer, and the lids serve as insulators of different materials, for example. If you remember from the previous lessons on manually creating lids, we used a mid-plane option for the extrusions when creating the lids. Now, I mentioned that the reason for doing this was because using a blind option would create an invalid contact later on. Let's take a closer look at what this means. When we created the lids, note that by using either the Create Lids tool or by using the mid-plane option, we actually created what's known as a surface contact between the lid and the model. Notice how the outer surface of the lid is in contact with the outer area of the part. This is a correct surface contact. However, in this example, created using a blind extrusion, notice that the lid only maintains a line contact with the part. This line or edge contact is incorrect. The lids must have a surface contact in order for the flow simulation to be run. A great tool you can use to verify your lids and setup before creating the flow study is by running the Check Geometry tool. The main purpose of the Check Geometry tool is to inspect the model for invalid contacts, such as a line or edge contact, and also to calculate the internal fluid volume within the SOLIDWORKS model. Before running the simulation, your models must be checked by flow to make sure they can be meshed and solved for correctly, and also to ensure that there aren't any problems with the geometry that might prevent meshing. The two main reasons that prevent meshing are, number one, that there are openings in the geometry that prevent SOLIDWORKS from fully defining a fully closed internal volume. Now, this would happen only in an internal analysis, and only if there are openings that haven't been closed off by lids. The second reason a model cannot be meshed is invalid contacts. An invalid contact is defined as an edge, line, or point contact between the part files, like we saw earlier. These invalid contacts prevent SOLIDWORKS from being able to calculate the internal fluid volume, and you won't be able to run the analysis. Let's look at a couple scenarios. I'll run the Check Geometry tool by clicking the Check Geometry icon on the Flow Simulation toolbar. At the top, you can see a list of all of the bodies in the part or assembly. You have the ability to enable or disable any of the bodies by selecting or deselecting the checkboxes here. Make sure they're all enabled before running the tool. There are a few checkboxes for excluding regions of the parts and also for creating assemblies. In most circumstances, I recommend leaving these cleared. I'll make sure the analysis type is set to internal and click the Check button to run Check Geometry. The tool runs, and you can see the fluid and solid volumes and also a list of invalid contacts. If there were any invalid contacts present, we'd get a fluid volume of 0, and there'd be some invalid contacts listed below. This model checked out perfectly. We got a fluid volume of above 0 and no invalid contacts. There's one more tool I'd like to go over before we really start digging into creating flow studies. It's the engineering database. I can access the engineering database by going to the Tools, Flow Simulation drop-down. Here in the database, you can see the library of data and information that Flow has available right out of the box. You can use the tree to navigate through the database. As you make selections, notice items appear in the main database window. If you double-click an item, you can see its properties. The values for the predefined items are locked, but you might have noticed that there are user-defined folders in the database tree as well. Let's add a user-defined porous medium that we'll use later in the course. I'll expand the porous media folder, right-click on the user-defined category, and select New Folder. I'll call this folder Carburetor Air Cleaner. I'll insert a subfolder under the Carburetor Air Cleaner folder called Porous 0.95. Now, you don't need your file structure to go this deep, but I like to keep everything in the database very organized. I'll right-click on the folder and select New Item. You can edit any of these property values simply by clicking in the Value column and replacing or editing the information. I'll call this item Porous Medium. For the porosity, I'll enter a value of 0.5. I'll select the permeability type to isotropic and the resistance calculation formula to dependency on velocity. With this setting chosen, I'm asked to enter A and B values so SOLIDWORKS can calculate the permeability. The permeability follows this formula. K equals A times the fluid velocity plus B all over the fluid density. A and B are constants and usually provided by the porous media manufacturer. I'll enter 57 kilograms per meter to the fourth for A and 0 for B. I can exit the database, and I'm asked if I want to save the changes. I'll click Yes, and the database is updated to contain our custom information.